Good afternoon, students. Let us start the class. In the yesterday's class, I was discussing about how difficult it is to decode the encoded convolutional bit stream at the receiver. Because when there is a bit stream of length hundreds or more, then at the receiver, it cannot go for the exact decoding as it was doing earlier, and at the same time it cannot have 2 power 100 combinations. Let us say a bit stream is containing 100, then the receiver is supposed to have 2 power 100 combinations. Out of 2 power 100 combination, it has to find out whichever is the most likely transmitted code. That is not an easy task, for which we have a solution, and we are discussing today about how the receiving is going to happen, or how the decoding is going to happen at the receiver. Let me briefly read the same thing again. When the block length runs up to thousands of bits, the decoding of the same is a very tedious process. To alleviate this issue, the convolutional decoder takes soft decisions in which it determines the best possible sequence of transmission states that could have produced the parity bit sequence that was received. Such decoder is also called as maximum likelihood decoder. This means that from the set of possible transmitted messages, the code word with the smallest Hamming distance is the maximum likelihood one. So when R is the received code with parity bits and C is the corresponding code word at the source, N is the length of that valid code word, D is the Hamming distance between C and the decoded code word, and if P is the probability of bit in the BSC, then the conditional probability is given by probability of R/C is equal to small p to the power of D into 1 minus p to the power of n minus d, where d is the Hamming distance. Now, taking logarithm of this conditional probability, we get log of capital P of R/C is equal to d log of p by 1 minus p plus n into log of 1 minus p. Now, as the RHS in this equation is constant, because p is fixed, n is fixed. Now, only d is going to be the determining factor here. So, log of p R/C attains maximum value when d becomes minimum. When logarithm of this conditional probability is taken, it is called as log likelihood. Let us take an example here. Let the independently distributed bit error rate of a channel is 0.001. What is bit error rate, or BER? What does this value 0.001 mean? 0.001 is nothing but 10 power minus 3. Right? So, it is nothing but 1 over 10 power 3. Okay. Now, this means 1 bit error in 1000 bits. That is what is called as bit error rate. In 1000 bits, if there is 1 bit error, then the value is 0.001. So, that is the meaning here. Let me continue now. If the BER of a channel is 0.001 and the received sequence is 110101, presuming that the sender would have sent either 1100111 or 1100001. You can see here, let me underline. We have these 1101001. Here we have 1100111. We have 1100011. That means the fourth bit is having error here, and the fourth and the fifth bits are 5th and 6th. There is a 3-bit error in the first sequence. There is a single bit error in the second sequence. Now, the respective Hamming distances are 3 and 1. Therefore, as we have already seen in the previous equation, that capital N is constant and small p is constant. So, only that Hamming distance is the decisive factor here. So, the conditional probability for the first case is 0.001 whole cube into 0.999 to the power of 7 minus 3, using the equation which I showed you earlier. This becomes 9.96 to 10 power minus 10. And then for the second case, 0.001 to the power of 1, that is d or the Hamming distance, into 0.999 to the power of 7 minus 1. You can see the value in the upper case is 9.96 into 10 power minus 10. The value in the lower case is 9.94 into 10 power minus 4. Obviously, the second one is having higher probability compared to the first case. So this is what is called as maximum likelihood. So at the receiver, it can calculate the probability for the received sequence to be of equivalent to some other transmitted sequence, and if the probability is the least, then that is the maximum likely code word that is sent. So thus it can be seen that the second sequence is overwhelmingly more likely than the first one. Therefore, given a choice of possible transmitted messages, the decoder should pick the one with the smallest Hamming distance. So that is what the decoder decides. Whichever is having the smallest Hamming distance, that will have the least probability of error, and whichever has the least probability of error, that is going to be maximum likelihood code with maximum likelihood. As I told you yesterday, it may be impossible to completely detect the error and correct the error that way. Instead, what can be done is calculate the probability, and based on that, select the code word which is having the least probability. Then there is no need of detecting the error also, there is no need of correcting the error also in this case. Now, if detecting and error correcting has to happen, then lot of time is going to be utilized at the receiver because the bit stream is large number of bits. So, however, as mentioned earlier, in case of convolutional coding, the list of possible transmit sequences is enormously large. As a sequence of n bits will have 2 power n possible strings. If the stream is having 100 bits, it will have 2 power 100 possible strings. Now, in such a case, how the receiver will detect a particular code word? This is again another complication. Let us see the solution now. For example, when n equals 256, there will be 1.1579 into 10 power 77 strings. N equals 256, it will be 2 power 256, that is 1.157 into 10 power 77. Now the receiver cannot have these many strings in its storage, right? Now this will make the decoding process horribly intractable. Intractable means we cannot be able to have a tractable algorithm here. In fact, in the computer science domain, they study a different course called Analysis and Design of Algorithms. There they have many solutions and they have many graphical approaches. There is one algorithm called Dijkstra's algorithm. There are many such algorithms. They decide between the intractable algorithms or intractable solutions and how to obtain the solutions which are feasible. If I have to give an example, right now this corona pandemic is an intractable problem, which means we don't know when it is going to end and we don't know when this situation will improve. Now, what is the possible solution? The possible solution is take all the safety measures so as to safeguard oneself and take other alternative measures. So, whenever we have intractable problems, but the problems are bound to be solved in one way or the other, we will have to go for some other solution. So, let us see the solution today. This process is going to be horribly intractable. Therefore, to perform this decoding process faster, a powerful and widely applicable method called as Viterbi decoding is used. Remember this. We are going for a different method called Viterbi decoding. I showed you the state diagram in yesterday's class. We are going to make use of the state diagram now. Viterbi decoding is used, which uses a special structure called as trellis. Later on, I am going to tell you what is meant by trellis. I am going to show you that also. This structure is derived from the state machine. And in the trellis, each column has the set of states. Trellis diagram will have lot of columns, and each column will have the set of states. Now from state to state, when a transition is happening, there can be the next column. For example, for the example state diagram given earlier, each state in a column is connected to two states in the next column. I will show you that. So in this state diagram now, each state 0, 0 is connected to state 1, 0 also and state 0, 1 also. You can see that way. Each state 1, 0 is connected to state 1, 1 also, state 0, 1 also. So in this state diagram, each state is connected to the next two states. So we can represent this state diagram's transitions as columns. That is the idea here. So now the state in one column is connected to the state in the next column by means of lines. Here, out of each state, the top link is for the parity bit output that corresponds to input 0, and the bottom link is for the parity bit output that corresponds to 1. That way we can write the trellis diagram now. Out of each state, one is for the parity bit 0, one is for the parity bit 1. Let me show you the diagram once again. You can see one for the parity bit 0, one for the parity bit 1. Again you can see one for the parity bit 0, one for the parity bit 1. You can see everywhere one for parity bit 1, one for parity bit 0. So this way we can connect all these columns by means of these paths. So the example is shown below for the message 101, 100 and the corresponding parity bit sequence is 1111, 0100, 0110. This example we had seen earlier about generating two parity bits. When the decoder gets a sequence of parity bits, with the help of the trellis, the decoder can traverse through the trellis. Means let us say, now this is the received sequence. Now the decoder has to have this trellis diagram in its library, and it will traverse through the trellis and can determine the best path which represents minimum or no error. Let us say in the trellis it is going to find out this path. Each state is represented there, and state to state transition is also connected there in the state diagram where there are columns now. In the said example, as we have 4 states, we will have 4 columns now. So the receiver has to simply go through the trellis path each time when the bit stream is received, and it has to search for the best path there. Now these are called pathfinding algorithms. Pathfinding algorithms are extensively used in technology, whether it is routing in between two communication terminals, or whether it is routing in case of a VLSI designs, automated layout. There are so many algorithms that can be put into usage or put into application. That is why I have been telling you earlier also, it is the computer science people who develop these algorithms and produce such softwares for the applications, and the other people are going to use those applications. In our own case, Cadence tool which we are using in our library is not actually designed by electronics engineers. It is basically designed by computer science engineers. We are using it. So that is called pathfinding. So here also, in the case of trellis diagram, the decoder can traverse through the trellis diagram and it can determine the best path, and this best path may represent no error also, or it may represent minimum error. It has to go through all the paths to find out the best path. Now how it goes through that path is based on this sequence only, right? Now when it is receiving this, it will go through this 111101000110. Let us say in the trellis diagram it exactly finds the same path. Then it means there is no error. Now it may not find the same path. Then the decoder has to make a decision when there can be minimum Hamming distance between these two. The such path which it finds which will have minimum Hamming distance, that itself is the maximum likelihood algorithm. So as an enhancement, the Viterbi decoder finds a maximum likelihood path through the trellis structure. I am showing you one diagram here. You can see the states are 0, 0, 0, 1, 1, 0, 1, 1. Now as per the state diagram which I have shown you earlier, you can see this sequence 1, 0, 1, 1, 0, 0. Now you can see for 0, 0, 0, 1, 1, 0, 1, 1, after each state, you can see the path. There are many paths connected. That means all these columns are connected by means of such transitions. All the gray lines are the transitions between state to state, because there are 4 states. In between them, always there is a transition based on the input is whether 0 or input is whether 1. Now based on that. Now when input is 0, from the state 0, 0, it is going back to 0, 0. If the input is 1, from the state 0, 0, it is going to a state 1, 1. So that way, no, 1, 1 is the output parity bits. It is going to a state 1, 0. This 0 slash 0, 0 is the input bit and the output bits actually. 1 slash 1, 1 is the input bit and output bits. Whereas from 0, 0, if the input bit is 1, output parity bits are 1, 1, it is going to the state 1, 0. So in this manner, you can see this trellis diagram with all the paths is present at the receiver. That is the point here. There are so many paths here now. This is present at the receiver. Now when the code is received, for example, when the code is received, the code is received is 101100. When the code is received, initially it is 1 here, okay, then it is 0 here, then it is 1 here, you can see, then it is again 1 here, again there is 0 here, and then finally 0 here. So as soon as the receiver receives this particular code, it has to go through the diagram such that it will find that path there. If it finds the path there, then that's all. Which means in this particular case, there is no error at all. Why? Because it has found the path which corresponds to the input bit stream. But in this case, it is only 6 bits. If there are large number of bits, there can be larger number of paths. Only thing is, immediately what the receiver can do, it can follow the same sequence which it received. Maybe at some point, it may not be finding a path. Let us say, just to give an example, here this 1 is there. Let us say in the trellis diagram, that path may be missing. I am talking about millions of paths, not just these 6 bits I am talking. Let us, there is a very lengthy bit stream and there are millions of paths. All the paths may not be stored at the receiver. It is impossible, as I told you. It becomes intractable. If at all we have to save 2 power n paths there. So that is where the ingenuity of the designer comes into picture. At the receiver, how many paths are going to be stored in the trellis diagram? Now, let us say this 1 is not there. Instead, only 0 is there. Let us assume that way. Now, it will go through the path of 0 only. Imagine. It will go through the path of 0 only. Later on, let us say there is a path corresponding to 0, path corresponding to 0. That means there is a 1-bit error now. It searched this path 101000, which means there is a 1-bit error. But if at all your received vector is having 100 bits, in that if 1-bit error is there, it does not matter much. I gave you many real life examples yesterday. So it does not matter much. That is why this is a maximum likelihood algorithm. So now this is the way. This is a very special way of actually not at all detecting the error, not at all correcting the error. Just traversing through the trellis diagram for finding a path which corresponds to the received vector. If there are, let us say, 1 or 2 bits of error or little more also, it does not matter. Let us say the input stream is 1000 bits, even if 10 bits error are also there, it doesn't matter. As I showed you, BER is what? Bit error rate is 1 over 10 power 3 means 1 bit error in 1000 bits. It does not matter actually. We should still say that the communication is of good quality. So this is that particular trellis diagram. Now what is the requirement at the receiver? At the receiver, it requires large amount of memory to store this trellis diagram, which is corresponding to the bit streams that are received. Now that is the complication. But the point here is, in the VLSI era, memory is not expensive now. Memory is cheaper now. What is expensive now? What is expensive now? Time is expensive now. Everywhere we want applications to be processed faster, tasks to be completed faster. So, the most expensive thing in 21st century is time, not money. Money is also abundant now. Memory is abundant now. Almost everything is abundant, only time is scarce. So at the receiver, if at all it has to save these many paths, it requires a large amount of memory, and large amount of memory is possible. For that purpose only we have VLSI engineers, ULSI engineers. Their job is to keep on producing new types of memories with better technologies. So if that memory is available at the receiver has to immediately have a tractable algorithm here by finding the path in the trellis diagram. So that way it is an easy task, faster task. For this we have something called Viterbi decoder. I have told you the method of convolutional decoding at the receiver. Now let us see about the trellis diagram itself. Let us see what is the meaning of Viterbi decoder. This method of decoding avoids the explicit enumeration of the 2 power n possible combinations of an n-bit parity sequence. That is obvious. When there are no errors in the received bit sequence, one particular path through the states of the trellis would be matching exactly with the transmitted sequence, as we had seen in the example earlier. In that path, the concatenation of the input bits of the particular states corresponds to the transmitted sequence. But in practical situations, as there are errors bound to occur and as it is cumbersome to traverse with the 2 power n paths, it is desirable to find the most likely path through the trellis that will introduce minimum BER. I was telling you the same thing. We cannot have 2 power n paths at the receiver. I told you about 2 power 256, which is impossible. Now we will have to have only those many paths at the receiver which will introduce minimum bit error rate. Now for the purpose of decoding, the Viterbi algorithm uses two metrics known as branch metric and path metric. The branch metric utilizes the Hamming distance as shown in the figure. You can see here, these red colored numbers are basically branch metric. Remember, branch metric we give a notation as BM. For path metric we give a notation of PM. Now you can see this BM utilizes the Hamming distance. Now from this 0 0 we can have 0/00 and then we can have 1/11, as I mentioned, corresponding to the input bit. Those are the parity bits. Now what are the 0 2? What are these 1 1 2 0 1 1? These are the branch metrics indicated there. Let me show you in the next explanation. In the figure, for the received sequence 0 0, the red colored number on the arc shows the BM. The PM or path metric utilizes the paths with the smallest Hamming distance as they correspond to minimum BER. For finding those paths, the predecessor states are utilized. For example, for the state 0 0, the two predecessor states are 0 0 and 0 1 itself. If you remember the state diagram, it used to go back to same state when the input bit was 0. it was go to the next state 0, 1 when the input bit was 1. So the predecessor states are labeled as alpha and beta, and they are always the same for a given state. For the state 0, 1, the two predecessor states are alpha equals 1, 0 and beta equals 1, 1. This is all with respect to the state diagram which I have shown you earlier. Now in the figure for the received sequence 0, 0, the red colored number on the arc shows the branch metric. Let us see that. The received sequence 0, 0, for which there is a branch metric of 0, 2 and then 1, 1, then 2, 0, then 1, 1. What is this branch metric? It is utilizing the Hamming distance. So based on the Hamming distance, for this sequence it will have 0 Hamming distance. For the next one you can see Hamming distance is 2. Why? 0, 0, 1, 1. So between 0, 0 and 1, 1 distance is 2. Next 1, 0 distance is 1. 0, 1 distance is 1. 1, 1 distance is again 2. 0, 0 again 0. 0, 1 is 1. 1, 0 is 1. That is the Hamming distance, which itself is indicated as branch metric. Now using the branch metric, the decoder has to utilize the Viterbi algorithm for the path metric, and the path metric should correspond to minimum BER. So the PM utilizes the paths with the smallest Hamming distance as they correspond to minimum BER. We can see here minimum BER is there here 0, 0 and here 0, 0. We have minimum BER. Actually no error at all. Now with the 1, 0, 0, 1 and 0, 1, 1, 0, we have Hamming distance 1. Now in this particular case, all the sequences are summarized because it is hardly 4 states. But in a large number of states, more than 1000, it may not be possible to have all these paths defined at the decoder. So the point is what? Let us consider only the minimum Hamming distance paths. Let us ignore all those paths which are having the larger Hamming distance. For example, if you have to implement this particular diagram using trellis diagram at the receiver, we can ignore all those paths which are having the Hamming distance 2, right? Because it is not probable that when the 0, 0 is transmitted at the receiver we will have 1, 1. That probability is less, right? So that way at the decoder it can simply remove all those paths. It need not have all those paths in the trellis diagram which are having the Hamming distance which is larger than the minimum Hamming distance. That is the idea here. Anyhow, we know that there is a lesser probability of having larger number of errors in the bit stream unless it is a burst error. If it is a burst error, there are other methods that are going to be followed. Apart from that, there is no chance that if 100 bits are sent, out of the 100 bits, there can be 50 bits at error, or even 40 bits at error, or even 30 bits at error. So what we do? We need not have all those paths, 2 power 100 paths at our decoder. We will discard all those paths which are corresponding to the larger Hamming distances. We will have only those paths which are corresponding to the minimum Hamming distances. That is the idea. For that purpose only we have this branch metric and path metric. So if S is the state and if I is the time step, then at time step I plus 1, we will have path metric of S comma I plus 1 equals minimum of path metric of alpha comma I plus branch metric of alpha tending to S, and path metric of beta comma I plus branch metric of beta tending to S. This is a general expression. Proceeding this way, when once the path with the minimum Hamming distance is found out, this path needs to be traversed from the final state to the initial state, and by reversing the order of the bits, the most likely message is obtained. Thus, the procedure for finding the most likely path is as follows. Add the branch metric to the path metric for the old state. Compare the sums for the paths arriving at the new state. Select the path with the smallest value, breaking the ties arbitrarily. The selected path will be one with the minimum errors. Now the procedure is as shown. There are many diagrams here. I am just showing you the procedure here. Now let us say we have these 111011000110 as the stream. Now starting from this 0, we can traverse this way. You can see the received one is 1 1 now, right? Received one is 1 1. You can see it here. Now corresponding to 1 1 from state 0, let us say there it was 0 0. We will have this branch metric now, where we have Hamming distances listed 2 0 1 1 0 2 1 1. You can see it listed. Now obviously that 2, see, we have that 2, then we have that 0, then we have again 0. Now this is an example where 1 1. Now from 0 there is this 1 1 Hamming distance 0. Okay, again there is this 2. Now again 1 0, there is also 1 0 2, let us say 1 1 Hamming distance 0. And again here also Hamming distance is 1. This way we can list out all the Hamming distances in each traversal. In each traversal, and all these red lines are indicating that particular traversal. We can proceed this way, discarding all the paths which are having the maximum Hamming distance. You can see here in the next stage, red lines are missing there, discarding all the paths which are having the maximum Hamming distances. That way we can proceed one by one to the next states, and finally you can see we have arrived at the last column now, and here you can see the path is there corresponding to 1 1 1 0 1 1 0 0 0 1 1 0. Now if at the receiver it follows this particular path, there is no error now as such. This is how Viterbi decoder need not have those paths now. Now the example is all those red colored paths are removed now. Finally means wherever the corresponding Hamming distance is 2, such paths need not exist at the receiver at all, because it is highly improbable that such errors will occur. So in that way, at the receiver, this is the Viterbi algorithm. Viterbi algorithm basically uses branch metric and path metric, and it removes all those paths which will have the larger Hamming distances. It will retain those paths with the minimum Hamming distance. In that way, when the receiver receives the bit stream, it will go through only those many paths, because the other paths are not at all existing. So it can be a quicker job at the receiver. This is called Viterbi decoder. Now Viterbi decoding is widely used in modern disk drives, speech recognition systems, natural language systems, and a variety of communication networks. However, the limitation is that the computation complexity is exponential in the constraint length. We are seeing the constraint length here, right? For example, here what is the constraint length now? 2 plus 2 plus 2 plus 2 plus 2 plus 2. So it is totally 12. Now, when the constraint length is 12, now this algorithm is exponential as far as computation complexity is concerned. The meaning of computation complexity is all these algorithms are basically pathfinding algorithms. Now let us say from Bengaluru you have to go to Mysuru. If from Bengaluru you have to go to Mysuru, you will either go through Kanakpura or you will go through Ramnagara, or you can also go through Kunigal and via Melkote also. There are many paths now. Which path will you choose? You will choose the best path which will take you there earlier with minimum effort. Now, instead of you choosing the path, you will ask Google only. You will go to Google Maps and you will check. Now, depending upon the live situation, the Google Map will search the path. Now, just think about how Google Map gives you the path instantaneously that way. Within a few seconds, the Google Map shows you the path. How? Google Map is also utilizing these pathfinding algorithms. With all the real-time data, the Google Map is applying that algorithm immediately, and it is going to immediately show you on your mobile screen, which is a wonderful application. I used to keep on telling in the classes that transistor is the 8th wonder in the world, mobile phone is the 9th wonder in the world, Google Maps is the 10th wonder in the world. In fact, Google Earth, I used to tell earlier that Google Earth is the 10th wonder in the world, because in Google Earth, we can actually see the surface view, we can actually see all the buildings also through the Google Earth. In the Google Maps, it is going to only showing the locations and the paths and the probable time of your travel. But in the Google Earth, you can actually see those places as they are existing on the surface of Earth. So, how this Google Maps is working? It is immediately going to use the pathfinding algorithm. So, in any such pathfinding algorithm, when the number of paths are increasing, the computation complexity is exponential. Why? More the choices of moving here and there, now it has to move through all the paths, right? Now this particular Viterbi algorithm, right now I am showing you only a 12-bit sequence, and it is easy. In the trellis diagram, it is easy to look at this path. It does not take much a time. But now when the number of bits increase to 100, to 1000, there is a computation complexity. Means quickly it has to go through all the paths as such. Now that computation complexity can be exponential. How to solve? If the computation complexity is exponential and we want to have a quicker search, how to solve? Any idea? I hope you got my question. Let us say in this example it is only 12 bits. Let us say we have 100 bits. Now in case of 100 bits, let us say using all this branch metric and path metric, the receiver has kept some paths which are having minimum Hamming distance. But still, there may be many paths having the minimum Hamming distance also. Now, in such a case, when there are multiple paths with minimum Hamming distance, it has to choose one of the paths. Means it has to go through all the paths now. That is when the computation complexity is going to be exponential. How to solve? Anybody can answer? How can I have a quicker solution? I hope my students are listening. At least 18 students are there. Okay, the answer is at the receiver have multiprocessor systems, not just a single processor. Have multiprocessor systems. Instead of one laborer working on a particular task, let there be two laborers working. That is how at the receiver, if there are multiprocessor systems, now together they can traverse different paths, and the best path can be immediately selected at the receiver. So nowadays, to reduce the computation complexity, we should have multiprocessor systems. That is how we have quad-core, octa-core computers, right? You might be already familiar with the ARM architecture, Advanced Risk Machine Architecture. You might have already heard the names of Cortex series microcontrollers. And now we have quad-core, octa-core microprocessors. That is basically to reduce the computation complexity. That is why I told you VLSI engineers and ULSI engineers are meant for that, to keep on designing high-speed memories, high-speed processors, so that these, whichever is the algorithm that is tractable, that can be implemented in spite of the constraint length remaining larger. So this vector decoding is widely used in the modern disk drives because from the disk the information is going to be transmitted as thousands of bits. In the speech recognition systems, for example, when the speech is converted into digital, let us say my speech right now is an analog speech waveform, that waveform is converted into digital. Now that will correspond to a particular bit stream. If speech has to be recognized, in your mobile phone also nowadays you have speech recognition, which means you will speak into the phone and the phone will function accordingly, right? There are many robots which can detect a particular person's voice. For example, in future, instead of a doorbell, you stand in front of the door and you speak into the door. If you are one of the family members, the system itself will automatically recognize your speech because your speech is already stored in the database and the door can be automatically opened. Even in the car, without having the key also, you simply speak into the machine and the car can open its door. That's a speech recognition system. But lengthier the speech, larger the stream, more is the complexity. So it is better to use viterbi decoding there. And speech recognition is always connected to natural language systems also. Language is nothing but extension of speech itself. And a variety of other communication networks. In fact, viterbi decoding is used even inside the mobile phones. I was telling you about a chip called vocoder, voice coder. In the vocoder, there is a viterbi algorithm utilized at the receiver side. So the limitation can be overcome only by means of multiprocessing systems. Now with this, I have come to the end of the 5th module and we have covered the syllabus completely. So from the next class onwards, I will go for the discussion of the additional exercises which are present in each module and we will revise the course once again briefly. So for today, I am going to end the class. With today's class, we have ended the syllabus. In the next few classes, we will have the revision briefly. See you in the next class. Until then, take care and goodbye.